Hello students! In this video, we are going to discuss the guided study for learning target D4. That is basic differentiation rules. In this section, we are going to differentiate functions using the constant multiple, sum difference, and power rules. We will also differentiate some other types of functions, specifically base E exponentials and the natural logarithm function. To begin, let's discuss the notation that we will use for derivatives, and we've kind of already seen this notation. As a reminder, we discussed previously the limit definition of the derivative, and when we did so, we were given a function like y equals f of x, and when we differentiated it, we wrote it as y prime equals f prime of x. The prime is the notation for the first derivative. As you increase the number of derivatives you take, we call this higher order derivatives. In this case, you can take a second derivative, and when you see that denoted with the double prime, it's also stated as f double prime. You may take a third derivative, and that will be with 3 little prime symbols. And a lot of times you will hear that referred to as f triple prime, or the third derivative. However, as you go to the fourth and higher derivatives, the notation changes. You'll see the number written in parentheses instead of the primes, which makes sense because you don't want to have to keep writing a prime over and over again as you get up to, say, the 60th derivative. That'd just be ridiculous. So we put a number in the superscript in parentheses, so that hopefully kind of helps distinguish it from a power. A few other notations you may see, again, given a function like y equals f of x, you may also see dy dx, or you may see d dx of f of x. And the way I'm saying it is the way that it's read. And what this tells you is the variable with which you are taking the derivative with respect to. So if, say, we ended up having a function that was y equals f of z for some reason, you can find y prime by differentiating with respect to z. This is less of an issue in single variable calculus, which we are in, than in multivariable calculus. In multivariable calculus, calculus 3, this little letter in the denominator of what looks like a fraction with d, d, z in it tells you which derivative to take. For now, we are in single variable calculus. We're going to stick primarily with variables of x as our independent variable. Another notation you may see that is another one that's a little more common in calculus 3 is a subscript letter next to the function name, f sub xx. This is going to be the second derivative with respect to x. We, in this class, calculus 1, are going to stick to this notation. You can also translate those two notations that I just showed you into higher order derivatives, but again, for the sake of Calc 1, we will stay with this. Now, there are many basic rules for differentiation, and I remind you that in Learning Target D1, we discussed the limit definition of the derivative. Now, the limit definition of the derivative required a lot of algebra, and you had to make sure that you simplified things nicely, and I'd say that it takes about 10 times the amount of time that some of these rules will take. To motivate this, however, let's talk about the constant rule for derivatives, and I ask you the question, what does the graph of y equals 2 look like? Well, the graph of y equals 2 has the y value of 2 for all x values, so it's just a straight horizontal line. What is, then I ask, the rate of change of the graph of y of 2, or y equals 2, from x equals 0 to x equals 3? Well, since we're asking for the rate of change, you could definitely calculate this as delta y over delta x, or f of b minus f of a over b minus a, just like we did in Learning Target L1. the rate of change of this function between 3 and 0, or 0 and 3, would be the function evaluated at 3 minus the function evaluated at 0 over 3 minus 0. The function evaluated at 3 and 0, however, are exactly the same. We've got the function y, or f of x, equals 2. So in that numerator there, we've got 2 minus 2 over 3, or 0 over 3, or 0. And this is kind of a proof for a derivation of why the constant multiple rule, or nope, not the multiple, but just the constant rule for differentiation is true. If c is a constant, any constant, then the rate of change between two x values, any x values, is going to be 0. So if I say find y prime given y equals 6, then your answer is y prime equals 0. Note the notation here. I have d dx of c written, where I have stated that c is any constant. So another example, the derivative with respect to x of 4 is 0. Next, we have the power rule for differentiations. Now, n can be a real number, any number. And a lot of times when this is taught at first, we start with whole numbers or even natural numbers before we step that into possibly using numbers like fractions, like you see here in the example. So we are going to recognize the pattern that we see here, and I'm going to give you all, or you will see, numbers with powers. They don't have to be whole numbers. They don't have to be integers or natural numbers. They can be any real number. Any number that you can subtract 1 from, really, in Calculus 1. So if I give you something like d dx of x squared, then what you have is n equals 2. So if you note that n number and you pay attention to the pattern, I emphasize this a lot in Calculus 2, this n is going to come down out in front. So I'm going to bring this 2 down. And then I still have my independent variable x, and its new power is going to be a value reduced by 1. So where it was 2 before, it's going to be 2 minus 1. So if we simplify that, we get 2 times x to the 1, or of course with those 1 exponents, just like coefficients, when they're there, we typically don't write them. You can. It's never an issue to write them. If you want to keep it safe, play it safe, then keep them written. But again, the power does not have to be an integer. It does not have to even be a natural number. It can be any number. So in this case, n is 3/2. We're going to bring the 3/2 down out in front. And then that power is going to be 3/2 minus 1. As a reminder, adding and subtracting fractions, you want to find a common denominator. This number 1 is like 1 over 1, so we can write this as 3 over 2 minus 2 over 2, and then subtract the values in the exponent of the fraction. So we have 3/2 x to the positive 1/2 as our final derivative. Now that exponent is not a 1, so we definitely want to keep it written. Next, we have the constant multiple and the sum difference rules for differentiation. The constant multiple rule simply allows us to treat a constant number in front of some function as if it really weren't even there. What we'll be able to do is take the derivative of the function that the constant multiplies, find that derivative, and then multiply the constant by the function's derivative after we compute it. So just like our example above, where we had the derivative of x squared, so recall here that we found above d dx of x squared is 2 times x to the 1. This means that when we evaluate the derivative of 4 times x squared, we can bring this 4 out in front and then multiply it by the derivative of x squared. Now, as far as all the notation and showing all the work, I will continue to encourage you to write all of the steps as you're learning this stuff. But it isn't necessary really to write this. And as you practice, as you practice, you'll start to get the hang of doing this multiplication really without even thinking about it. So we know that the derivative of x squared, we found it a little while ago. We know that this derivative is 2x to the 1. So you can see how I'm writing it there in the space that's green. And then I'm indicating that I'm about to multiply it by 4. 2 times 4 is 8. So we have 8x is the derivative of 4x squared. Now, here is the point in time in our video where I remind you to pull up the Desmos activity that accompanies this guided study. The Desmos activity that accompanies this guided study goes just about in order with the material that I'm covering. And in that guided study, you will see a question that asks you for a code word for this guided study. In that blank, please type the words red hawk. In the blank where I ask you for the code word, I know it's 2 words, but I picked the word and it's 2, please type the words red hawk. Continue with that guided study as you continue through this video. And at the end, you will see a chart with some basic differentiation rules that are useful from this section. I would highly recommend that you write these in your notes. They will also be in this notes document, of course, and our notes document that we will cover in the lecture for D4. However, it's not a bad idea to write these down, maybe fold them up and put them in your wallet, carry them around with you, and review them periodically. You will want to write them on your note card for your formula sheet, for your checkpoints for this course as well. Now, the last rule for differentiation we're going to learn is called the sum difference rule. Now, the sum difference rule isn't really too elusive. It just says if I add 2 functions together and I want to find their derivatives, then I add the function's derivatives. It feels a lot like distribution over addition for functions like 4x plus y. Right? We distribute that 4 in. This is 4x plus 4y. It feels a lot like we're distributing the derivative operation. We're not technically doing so, but if that idea helps you see what's going on, please use that. So as an example, we're looking at 2 functions added together, one that we've already differentiated. Remember, we differentiated x squared, got 2x, and then we differentiated 4x squared by taking the derivative of x squared and multiplying it by 4. So we know from above what this derivative is. But what this rule is saying is that, yes, I can take the derivative of 4x squared, and that's really the first part of this problem, because then I need to take the derivative of x to the 44th. I know this one, right? I used the constant multiple rule to help me break this one down and evaluate it. So I will evaluate it, or since we already have, I'll go ahead and write it. It's 8x. And then I will differentiate the second function, noting that in this case, n equals 44, and I'm going to apply that power rule. d dx of x to the n is n x to the n minus 1. So I'm going to bring the 44th power down out in front, multiply 44 by x to the 44 minus 1, making my final answer for this derivative problem 8x plus 44x to the 43rd power. I want to make a note, and I will mention this in lecture, that it feels like we're distributing the derivative operation over these 2 functions. We're going to have to be very cautious as we move forward. We cannot distribute the derivative operation over multiplication or division. We will learn the product rules and quotient rules in D5, learning target D5, to cover that. Last, I just want to state the derivatives for the base e exponential and the natural log function. And these are formulas. If you reach a point where I'm asking you to take the derivative of one of these functions, you may just write the derivatives. And it is the case that the derivative of the base e exponential is the base e exponential. We like to say the base e exponential has itself as its derivative. The natural log function, which is, remember, the inverse of the base e exponential, the derivative of that function is the function 1 over x. And remember, for the natural log function, it is implied that x is bigger than 0. So when we are asked to differentiate sums and constant multiples of base e exponentials and natural logarithm functions, we may, at first, desire to write this out step by step, where we pull constants out and we quote-unquote distribute the operation of differentiation over the sum we see here. And then we just note that in two places we're seeing a evaluation of something like d dx of e to the x or d dx of natural log of x. So this is going to be 2 times the derivative of e to the x, which I said is e to the x. The base e exponential is its own derivative, plus 1 over x. Now, I encourage you to, when you can, simplify things, right? But in this case, we can't really do much here. We're going to leave this as is. You could bring this exponent to the numerator as a negative, but don't for right now. And last, we will mention very quickly higher order derivatives. And as I mentioned before, a higher order derivative is just another derivative on top of potentially the first. So when we write f prime, what we're doing is we are evaluating the derivative of the first derivative. So we're taking d dx of f prime. And typically we will denote an nth derivative with, again, that number in parentheses. It looks like an exponent, but because the parentheses are there, it hopefully is distinguishing it from an exponent for you. And all the nth derivative is the derivative of the n minus first derivative. So the 6th derivative is the first derivative of the 5th derivative, for example. Now, this example asks us to find the 3rd derivative of the function that we just differentiated. So actually, what we can do is we can copy and paste this, bring it down, and write, okay, I'm happy because I found f prime of x here. But the 3rd derivative means we want f3 of x. So that means we're going to have to take the first derivative of the 2nd derivative. And with a 3, it's not as typical that we write the number 3. We actually do 3 primes there. So the 3rd derivative is going to be the first derivative of the 2nd derivative. And of course, the 2nd derivative is the first derivative of the first derivative. That would be the first derivative. We have the first derivative. We found it in the previous example. So we're going to evaluate f double prime as the derivative of that. Note that that's only the 2nd derivative. We still need to go one more time and find the 3rd. And I want to point out that the 1 over x function, we can differentiate. Now is the point where we're going to need to simplify that exponent a little bit. I keep doing that. E to the x there. So remember, there's an implied 1 written there. Just because it's not there doesn't mean there's nothing there. There is something there. There's a 1 there. And remember our exponent rules. If I have an x in the denominator of a fraction, I can bring that x to the numerator as long as I negate the exponent. And just as I said, these numbers don't have to be positive integers. A power of n equals 1 for our power rule is valid. So in this case, our first function, 2e to the x, its derivative is 2e to the x, right? And you can write it out just like we did before, if that makes you feel more confident. And I encourage you to as you learn these. In this case now, I'm going to be adding, and then I need to carefully follow my rule. N is negative 1. It must come down out in front, and then I must subtract 1 from the negative 1 in the exponent to complete my second derivative. In this case, f double prime is 2e to the x minus x to the negative 2. You can rewrite this as 2e to the x minus 1 over x squared if you really want to, but knowing we have to take the third derivative, we're going to leave it like that. So that when we go to evaluate f triple prime, we have d dx of f double prime, which is d dx of 2e to the x minus x to the negative 2. And then again, in that exponent, we're going to treat that as n equals negative 2. And when we differentiate this, that first function's derivative is once again e to the x times 2. And then we're going to subtract, and be careful about the arithmetic here, because we're subtracting negative 2 times x to the negative 2 minus 1. This turns into a positive every odd derivative. Watch out for this. And this is why I encourage you as you're practicing and as you're first learning this, if you are, then write out every little step so that you'll see that negative and not miss it. Keep practicing. Practice enough problems where no question can surprise you on a checkpoint. The final answer to f triple prime in this case is 2e to the x plus 2x to the negative 3. And you're welcome to rewrite this as 2e to the x plus 2 over x to the third if you would like. All right, that concludes the guided study for D4. I will see you all in the lecture for D4.